Hello. So in this video, we'll be taking you through second order system analysis. So second order system analysis basically is used is applied to study the dynamic behavior of systems such as circuits or control systems. It normally involves examining the frequency, magnitude response of systems, and it's often characterized by a transfer function with a second order denominator in the Laplace domain. The key parameters to analyzing second order systems is the damping ratio and the natural frequency. So in our system, this was the maths behind it. So as we can see, that is a transfer function of our second order system, where our A and B coefficients are, well, for start, the B coefficient is whatever you have on the numerator, which is 6,000,004. If I'm not wrong, that should be 64,474,532.56. So that's our B coefficient, B0, and our A coefficients are A0 would be 6, would be the same, and A1 would be 4030.3, and A2 would be 1. So that is a diagram, the circuit diagram that we came up with. The R1 and R2 values, you can see them there. 130 kilo ohms for R1, R2 is 4.3 kilo ohms. C1 would be 0.1 microfarad, C2 would be 470 picofarad, and our cutoff frequency for this system, we calculated it to be, with those component values, would be 981.9 hertz. The damping ratio is also seen there, is the last thing in the picture there. It's 0.195 or 0.2. So this is the circuit model that we came up with on LTSpice. We can see here that the circuit has an input there, which is an impulse, and the same components for the circuit are kept in place. The 130 kilo, 4.3 kilo resistors, 470 pico, and 100 nano. So after that, we implement a gain in the system of 0.2. If you do the maths there, the math here, 1k and 5k, you would get that the output on this end would be of a gain of 0.2. So that is the step response that we can obtain from running the simulation on LTSpice. We can see the graph goes from 0 all the way to 1, and at 1 second we can see the spike, and the step keeps going on forever. So that is the circuit diagram. That is the output diagram showing the gain on LTSpice. So if the gain is 0.2, that means we are essentially taking away from the input. Therefore, the gain would be negative, be a negative gain. So as we can see there, it goes all the way down to 20 microvolts after 1 second, and it stays steady for forever. So the next thing I'll be taking you over is the MATLAB analysis of the step response that we created on LTSpice. So as you can see, this is the diagram for the step response generated from MATLAB. You can see here on the y-axis we have the voltage, on the x-axis we have the time. Yep. And these are more diagrams to show you the phase response and the Bode plot of the diagram of the system that we came up with. Next we have the magnitude response, and we also incorporated an arbitrary input where we ran an input through the system, and we wanted to see the output after running the signal through the system. So that is the graph showing that frequencies. So that is the result we got from running a signal into the system. You can pause there if you just want to take a quick analysis. Right, so on this part of the presentation we have the A and B coefficients of the step response put into MATLAB. So the B coefficient is the numerator values and the A coefficient are the denominator values, as you can see here. So this command here, TF, is just the transfer function of we name the system SYS, and then we use the transfer function command using the numerator and denominator as the parameters for the command, and we can get this here, which is the continuous time transfer function. So all those diagrams and all those graphs were plotted using this MATLAB code here. Everything that you've seen in the past past minutes, past seconds, or as a result of this code here. So if I can just take you through it. The first line of code there just reads in the step response signal, which we created on LTSpice. So wherever you have that stored, you use the audio read function to just read it in. And this first variable here, the step response, is just what you want to name it. And FS is just for the FS here just represents so the FS here represents the sampling rate. Yep. So you could just pause the video here if you want to take a look at the code. Yep. So in this video here, this is just a short time lapse of the circuit being built. Right, so in that video I was just building the circuit. Right there we can see that we have the resistors in series. The resistors in series, that is a 130k. These two add up to 130k, and these four here add up to 4.3 kilo. So then we have the wire here going into the first capacitor that is fed into the output of the operating amplifier here, and then the other four resistors after the wire that goes into the capacitor here are the 4.3 kilo ohms that goes back down to the 470 picofarad capacitor here that is connected to the common ground. That also is fed into the op amp right there. Yep, so that's basically it for the building of the circuit. So that's the actual, that is the actual built circuit. So just to look at it in depth, we have here where you can see properly where the various components of the various circuit components, how they are built in. As I said, here we have the 130 kilo ohm resistor. We just had to use various resistor values because there are no definite resistor values that give you 130k, so you just have to add them up along with the 4.3k as well. So in the picture on the left here, we have when we have the probes inserted into the breadboard. Right here on the on row 26, we can see that's where we power our op amp, right there in that line. So this probe here is connected to direct voltage, DC voltage, 15 volts here and here. So on line 26, this whole line 26, we have the VCC plus, which is on this side here, and VCC minus, which is represented with the black here. Right. Well, so more on the actual build circuit. Right here on line 2, where we have the red wire with the blue probe, that is where our input signal from the signal generator comes in, say right there, and then the oscilloscope would display the output once the probe is probed into that line 23 there, which is our output for the op amp in that TL084 op amp here. So to connect to power the op amp with the plus and minus 15V, you have to ground. So you need two probes since the DC generator, let me call it just the generator, it has I think 3 channels. So you use channel 1 and channel 2, where in both channels, in channel 1 you ground the negative side, and in channel 2 you ground the positive side. So you have to obtain a common ground. You have to obtain a common ground for both channels. Once you get a common ground for both channels, now you have the positive and negative 15V, which you can now connect to your op amp right there. Thank you for watching this video. I hope this video would be of much use for future work that you might want to undertake when it comes to second order systems. Thank you.